I'm going to give a brief introduction about our today's speaker, Dr. Michael Gardner. Dr. Michael Gardner is an assistant professor at the University of California, Davis in the Department of the Civil and Environmental Engineering. He received his BS in Civil Engineering and his MS and PhD in Geotechnical Engineering from University of California, Berkeley. Before joining University of Davis, he was faculty in the Department of Geological Science and Engineering at the University of Nevada, Reno, and worked as a postdoc at the NHERI Center, where he developed software for natural hazard engineering. Prior to pursuing his graduate studies, he worked as a geotechnical engineer in San Francisco, and prior to attending the university, he served in the U.S. Army as a combat engineer. His professional and research interests include geological engineering, rock mechanics, natural hazard engineering, and the application of the numerical and stochastic methods to shallow earth processes, and also the engineering analysis. Today, Dr. Gardner will present on the topic of the fluid-solid interaction with the application in the natural and climate hazard engineering. He will explore how fluid-solid processes influence natural and the climate-related hazard, and how these interactions can be modeled to support research and real-world engineering practice. By this brief introduction, Dr. Gardner, the floor is yours. I'm going to stop also sharing.
Excellent. Thank you so much for the introduction, Parissa. Let me just share my screen here real quick. We'll see if Zoom crashes when I try and do this. Okay. Can everybody see that's all right?
Yep.
Yes.
That's good.
Okay. Great. Great. Let me start the presentation here. Okay. So like Parissa said, today I'm going to be talking about fluid-solid interaction, and specifically applications in natural and climate hazards engineering. And so for the presentation, I'll kind of start off first talking about dynamic fluid-solid interaction. And so here, different types of problems and how we might model it for this. First talking about rock scour, then I'll talk a bit about volcanoes, and then glacial firn from the climate side of things, and some current work that we're doing on this. And then I'll talk also a bit about some remote sensing work for flood hazard and how we can tie this together with some of these higher fidelity numerical models. So rock scour certainly is a fluid-solid interaction problem. And so I don't know, I guess 2017 to me feels like it was yesterday, but maybe folks here are young enough that they haven't heard about Oroville Dam. But so this near disaster, this occurred in California, in Northern California in 2017, when there was this warm rain on snow event that led to substantially larger inflow into the reservoir for this time of year. And so what happened was they were spilling some water, and it was not any substantial flow beyond what they've spilled before, but one of the concrete panels in this flood control outlet was scoured out, eroded out. And so they started seeing some dirty water, shut down flow to inspect what was going on. And so for the first time in the history of the reservoir, as the water built up behind it, water started spilling across this emergency spillway. And very quickly, things started to erode, and you can see these head cuts kind of making their way up towards the emergency spillway. And so if these cut back and undermine the emergency spillway, at this point, you could completely lose control of flow. So you'd have an uncontrolled outflow, which is really a very bad situation. And so this is what triggered the evacuation of about 190,000 people downstream of the reservoir. But so scour and this type of erosion it's not a new problem. Probably the poster child for rock scour is Rico Dam. And so this was in Spain in 1936. You can see this is an unlined rock spillway. The rock here, it's a really strong rock. The intact rock strength is very high. It's granite, but jointed and fractured. You can see the spillway gates, they were designed for about 4,000 cubic meters per second of flow. And over the course of about 2 years, at spills substantially less than what these gates were designed for, you can see a lot of material getting eroded, pretty quickly. So there's something here that's perhaps not getting captured in the way that these things are analyzed. And then another example recently, this is in Australia in 2011 at Ivanhoe Dam. And similarly here, there were larger inflows into the reservoir, but the discharges were not beyond what the gates were rated for. But there was a large amount of erosion. You can see these rocks that were picked up and eroded and deposited here. And so for scale, this is about 90 meters across. So these are big rocks that this water is moving. So I want to start off by telling you about some great experimental work that was done. And so this is Spalding Dam. This is up in the Sierra Nevada. So if you've got UC Davis is over here, this is in the Central Valley. San Francisco sits off to the west here. And if you go up here, the Sierra Nevada mountains, and then you've got Lake Tahoe over here. And so Spalding Dam sits up in here. It's a PG&E dam, is built in 1913, and the spillway here is unlined rock. It's granodiorites. Again, the intact rock strength is very high, but it has some fractures and jointing in it. And here we're looking at, this is spillway number 2. There's another spillway here, but this is the main spillway that's used. And you can see there's this slot that's been eroded here. And downstream is this large alluvial fan that's been forming over, about the last 100 years or so. I guess the formation of it has been expedited due to the spilling from this dam. So you've got over 75 Olympic swimming pools worth of material that's sitting down here. And these are not small rocks. Some of these are maybe the size of cars, and they're getting eroded by water coming across this spillway. And so here you can see a little more close up. This is what the dam looked like. Initially, the spillway looked like, I should say, the spillway in the 1920s, spilling directly onto the rock here. And then this is kind of what it looks like today, where you can see there's, can people see my mouse, by the way? I keep pointing with a mouse, but maybe.
Yeah, we can see the
Okay,
cursor.
cool. And so you can see there's been some upgrades to the gates, but there's also been some concrete repair work. And here's this slot that we could see from above. And so this was not here before. This was formed by the dam, putting the dam in there and then spilling across the spillway here. So again, the spills here are not enormous. They're well within what these gates are designed for, but something about the rock and the structure is making it so that it erodes. And so this is actually now, there's folks come and do rock climbing down on one of these spots over here. There's some good rock climbing thanks to the spillway. But anyway, so Mike George and Nick Sitar had this great idea to install instrumented rock blocks in the spillway in spots where blocks had been previously eroded. So you can see here's one of those spots, and here's Mike George casting this concrete block there that's instrumented. And so you're essentially doing a field scale test with controlled flow. So it was a really clever idea. And these 2 blocks were installed here, and both have since been eroded. So really an amazing study. In addition to that, they also did some scaled flume experiments where what they were looking at was how does the geometry of the fractured rock mass and the orientation of these blocks relative to flow change how easily they erode, essentially looking at the kinematics of scour. And so the experiment here, we're looking down on the top of the flume, water flows in this direction. And then you see this white circle here is a mold that could be rotated in flow. And then they put 3D printed blocks inside this mold and look at how that would change, how easily blocks would erode or not. And so I'll show you here quickly. I'll show you one of these experiments. Don't blink or you'll miss it. Okay, so it happens pretty quickly. Here's a slow motion version in case you missed it. And the thing I want to point out to you is you see initially the block is experiencing a pure translation along the intersection of these downstream faces. And then only once it protrudes sufficiently into flow do you start getting these hydrodynamic torques that pull the block out. So you get this transition from a pure sliding failure mode to a sliding and rotation failure mode. And so another experiment I want to show you here, this is some work by Dave Harbour and his students out on the East Coast at Washington Lee University, where here you've got these flat blocks sitting here. There's initially no protrusion, but you've got this hydraulic jump sitting right over the top of the blocks here. And so what you'll notice is that this block here starts to pop up. So you actually have hypereic flow, so flow within the fracture network that's going upstream. And then at this point where you have the lowest elevation in the water surface, that's where this protrusion is created. That block goes, now it unzips. You actually have these blocks sliding upstream, which is pretty wild. And then it just progresses from here. So there's this interaction between the fractures within the rock mass, the shape of the blocks, but then also what's going on with the hydraulics in terms of the water surface topography, if you have hydraulic jumps, standing waves, and this kind of thing. So given these experiments, really the goal is to try to be able to numerically model this type of phenomenon. And so here, really you have to describe the shapes of the blocks if you're going to capture the kinematics. So we're trying to account for the 3D shape of the individual rock blocks, and then coupling this with a fluid solver so we can actually look at this dynamic fluid-solid interaction. And part of this, a really important part, is that you get these dynamic pressure pulses from the turbulent flow over the top of the rock mass that injects these pressures into the fracture network and kind of helps jack these blocks up into flow. So here, really our steps were to develop a blocky rock mass model. So how can we model this? And then how do we couple this with a fluid solver so we can actually look at this process dynamically? And see here, our code is all open source. It runs in parallel because, as you'll see, especially if you want to resolve this in high resolution, it takes a lot of computational power. And so just brief overview about the model. So we're using the 3D discrete element method. And so we're using polyhedral blocks to represent these fractured rock blocks, which makes sense in the sense that you've got, the way these blocks form with the fracturing and jointing, they end up being relatively polyhedral. And then also what's nice about DEM is that it's modular in terms of how you describe your interparticle contact. It can be something as simple as linear elastic all the way up to like a Hertz-Mindlin type contact model. And so then we have to pair this with a fluid solver. And so that image is kind of on the bottom right illustrates this idea where you have your background fluid mesh where you're solving your fluid portion, but then you have this solid embedded in your fluid domain. And it can have large rotations, large displacements. So the coupling process is tricky. And so here we chose to use the lattice-Boltzmann method. And the reason for this is that coupling is handled in a relatively natural way in the sense that it's directly in your constitutive equations, compared to if you use something like finite elements or finite volumes, you may have to remesh quite a bit, which comes with computational cost, computational error, etc. And so then also these flows are highly turbulent. So we're using large eddy simulation. I'll talk briefly about that a little bit later. Okay, so just a couple slides just to give you some background on lattice-Boltzmann briefly, since I think it's somewhat, it's not as commonly used. But so essentially what we're doing is we're solving our fluid on this lattice, right? And so here I'm showing an example of a 2D and a 3D lattice. And so in this two-dimensional case, you've got this two-dimensional 9-velocity lattice, right? And so we're saying the fluid can only have velocity in one of these 9 directions. So either 0 velocity or one of these other 8. And then for the work I'm showing you, we're using a three-dimensional 27 velocity lattice. And then ultimately the equation we're solving is this continuous Boltzmann equation. But really what we're looking at is you've got advection on the left-hand side, and then you've got collision on the right, which you could think of in a way as somewhat of being a diffusive term. It's not exactly diffusion, but you've got these fluid particles that are colliding with each other and getting redistributed in space. And that's what's captured here. And so we're looking at the fundamental quantity we're solving here for is this F, which is the particle population. So we're not solving the macroscopic fluid behavior directly, nor are we looking at individual particles, but we're looking at this behavior of groups of particles. And so then essentially what we solve is this discretized version of the continuous Boltzmann equation, where you still have advection, and it's called streaming in lattice-Boltzmann, and then we have our collision term. So we end up solving a very similar form of this of the continuous Boltzmann equation. And so then just in terms of how we do the coupling, now since we have discrete element methods, we're using lattice-Boltzmann, and we need to kind of marry the two and have them talk with each other. And that's kind of shown in this image on the bottom right, where here we have some solid that's embedded in our fluid. And at some point, you'll have cells that are 100% fluid. You'll have some that are 100% solid. But then you have this transition zone where it goes, fluid to solid, and there's some mixture of both present. And so when we're looking at how do we account for the presence of the solid on our fluid simulations, we essentially get this equation where you can see it's still the same as what we had before. We still have streaming, we still have our fluid collision, but now we're multiplying it by some weighting factor, and we have this additional solid collision. And so really all we're doing when you look at this equation is it's just a time varying boundary condition where we're in our domain, we'll map at different times a no-slip boundary condition. And so if you look at this B term, when it goes to 0, the solid collision operator drops away, and we just have what we had before. But if it's solid, B goes to 1, so the fluid goes away, and you get this solid collision. And like I said, that solid collision, all it represents is just it puts a moving boundary condition that makes it that fluid can't flow through that and gives you a no-slip boundary condition. And then the source term here, this is just how body forces, so gravity, manifest in Lattice-Boltzmann. So once we've got the effect of the solid on the fluid, we also want the effect of the fluid on the solid. And the way that this works is we're essentially saying that each little cell that the solid is interacting with contributes some small amount of hydrodynamic force. And so what we do is we just sum all those individual little contributions, and that gives us the total hydrodynamic force acting on this particle. And then the torque is calculated in a similar way, except now you're just crossing it with the moment arm. And so that's how this coupling happens between the solid and the fluid and the fluid and the solid. So we really have dynamic coupling at each time step between these two different methods. And so, ultimately, once we've got this working, we want to actually make sure that it makes sense and can actually match reality. And so we modeled these flume experiments that Mike George and Nick Sitar did. And you can see here the Reynolds number, 50,000, so very turbulent. And here I'm just showing you snapshots of that video that we looked at before, where you see this transition of failure modes. And then I'm showing you snapshots from the numerical simulations, where these are 3D, and we've just taken a section through them to show you inside the fracture. But one thing I want to point out is that you can see we get this transition from a pure translation to a translation sliding failure, or sorry, a translation rotational failure. And it captures this automatically. We don't need to specify a priori what the failure mode is. Because we're capturing the shape of the particles, we're capturing the kinematics, and we're directly coupling it with a fluid solver. So we get what the actual hydrodynamic forces and torques are on the particle. It captures this naturally. And then when you look at the image here, the background is colored based on pressure. So blue is lower pressure, red is higher pressure. So you can see there's this high pressure on the upstream lip of this block. And you can see also these red and blue patches moving through the fracture network. So these are these dynamic pressure pulses, these turbulent pressure pulses that are helping jack and jiggle this block up into flow. Additionally, what I'm showing here is these are contours of the Q criterion, and we just use these to visualize what the flow structures are, these eddies within the flow. But essentially what they are is the Q criterion, it just, if it's more positive, it shows more vorticity dominated flow. If it's negative, it shows more viscous dominated flow, viscous stress dominated flow. But really we're just using that to visualize these flow structures, and you can see these vortices getting shed off the top of this. And really, I think the power of this method is that, if you're able to capture the physics, it allows you to make predictive analyses as opposed to having to constrain things. So I think that's really, for me, the novelty of this. And I want to show this here in the sense that we modeled these different configurations for what Mike George had set up in the flume, where we looked at different orientations of the blocks relative to flow. And what you see here in these plots below are the instantaneous location of the block center of mass. And so here, this on the x-axis is the x position, y-axis is the y position. And what you're looking at is the experimental data goes from white to blue over time. I should just do this. White to blue over time. And then the numerical goes from yellow to red over time. And so you can see we get in the numerical, we match the experimental, where the block initially moves upstream a bit and then moves along this intersection essentially of these two faces here. We similarly get the same type of response here for this configuration here. Yes, it's not exactly the same, but the numerics can't capture everything. But we are also looking on the scale of millimeters here, so it's pretty close. And then for this failure mode here too, and again, the numerics captures this without us having to tell it how the block will move or displace. It captures this automatically. Okay, so like I said, these simulations are highly turbulent. So we use large eddy simulation, and here you can see this is what this rock block looks like when it gets eroded. You can see here I've just made a little transparent, so you can see these three-dimensional flow structures all around the block. But the idea here is that, when you set up your numerical mesh for the fluid, you will have eddies in your flow that are larger than your mesh discretization. So you'll be able to capture that in your numerical simulation. But some of those eddies will be smaller than what you can resolve. And the thing is that when you look at how energy cascades from your large eddies to your small eddies, it's the small eddies that dissipate the energy. So if you don't capture that, you may run into numerical issues. So we use the subgrid scale viscosity model to capture that energy dissipation at the unresolved scales and how this energy cascades from the large eddies down to the smaller ones. So anyway, here's a video of what that looks like. And again, this is one block in the DM simulation, but we've got 2.5 million fluid cells. And so really to resolve this well, you need a lot of computational power. These things are getting faster, and I'll show you some recent results from some of my students. But so where we're currently at on this is, as I showed you in those videos earlier, capturing the free surface topography is really important. And so we're adding free surface to the lattice Boltzmann, where you have essentially this two-phase fluid, single-phase solid, but capturing the free surface, and then also doing adaptive mesh refinement. So we only have high resolution where we need it to get the fracture flow, but then not having as fine of a mesh elsewhere, so we can do more computations. And then we're also doing some collaborative work. This is a collaborative project with Dave Harbour out on the East Coast. And so here's just some prototype blocks. But so what we're doing is we're printing these 3D printed fractured block sets, where we're putting these in the flume and looking at how this three-dimensional fracture orientation, block shape, paired with the water surface topography play together to kind of make scour more or less likely. Here's some simulations from Jakob, who he ran these simulations recently. Let me just turn off this laser pointer so I can click on this. So we actually recently coupled. Now what I'm going to show you is these are some animations where you have three blocks sitting on top of each other. This is essentially a dam break, but it's lattice Boltzmann coupled with DM with free surface. And so this is what it looks like. So I think, do you have a question, Robin? Oh, I just see your hand up. Oh, okay. Sorry. Cool. So anyway, so this is some recent results. I think it looks really cool. I was really, when Jakob showed me this, I was very impressed. We still need to make sure it's actually correct. It needs to be verified and validated, because at the moment it's a pretty picture, but we still need to make sure that it's actually correct. But so that's the current state of these things. And so, I've been talking a lot about fluid-solid interaction for rock scour, but fluid-solid interaction is one of these things that shows up in many, many different realms. And so this one actually was not something that I'd thought about before, but when I was at Reno, a colleague of mine, we started working on this together. We're actually looking at volcanoes. And so these are the Chaos Crags in Lassen Volcanic National Park. So you've got these 7 volcanic domes sitting over here. And so if you look at these, what are called mafic enclaves, you can find them in these volcanic rocks, or if you've ever gone for a hike or a walk or so, and you see these more silicic rocks with these darker globs included in them, where you see this lighter, more silicic rock, and then these more magnesium and iron-rich globs. And you might have wondered, what the heck are these and why are they here? And so these are what are called mafic enclaves, and they essentially serve as these tracers of previous periods of volcanic unrest. And so if you look at this, if you have some magma chamber hanging out under the ground here, you can have this intrusion of this more magnesium, more iron-rich, so this mafic intrusion, which triggers volcanic eruptions, right? And so this gets intruded in here, and what may happen is these two magmas may mix and fully hybridize. Or you may get this case where they don't fully hybridize and they quench in this state where you have your more silicic rock, and then these yellow globs are these mafic enclaves. And so essentially these enclaves serve as records of this volcanic unrest. And so if we can learn from these enclaves, it essentially will help us understand individual magmatic systems and improve our ability to forecast potentially the response of these systems based on what we see in these enclaves. And so really, I'm not a petrologist by any stretch of the imagination. And so where I got kind of pulled into this is one of the questions is if you look at these enclaves, if you're going to try and interpret maybe what was going on from these different intrusion events and how things might have been triggered, how long is that signal that they're recording going to be valid for? And so really, how long do they survive within these different magmatic systems? And so you're looking at how crystals erode from this interface and how quickly this thing would get eroded. So we're essentially doing hydraulic plucking, but the viscosity is 4, 5, 6 orders of magnitude higher. The Reynolds number is also way, way lower. We're looking at like purely Stoichian flow. It's around 1 or less Reynolds number. And also we're looking at the individual crystal scale, where here we're looking at this interface. These are thin sections where you've got some clinopyroxene and plagioclase crystals sitting along this interface. And so we're interested in how they might erode. And so you can model that. And so here, these are some initial just simulations that we ran just to look at for different viscosities, different protrusions. But here, what you're seeing is this is what could be a plagioclase crystal or so getting eroded very slowly. Here's again the Q criterion. You can see it slowly getting pulled up. This is a low velocity flow, high viscosity. And the reason this thing looks kind of like a cuttlefish when you look at it, where it's kind of you can see the boundary kind of moving a bit. That's not because the particle actually looks like that. That's just the way that particle maps into the fluid domain. So that's a mesh resolution artifact. But anyway, so you can start looking at these different viscosities, crystal shapes, orientations, and then also if you look at different numbers of crystals, how they sit together, how quickly they might erode. And so you can start getting a sense of what the spread is for how long these enclaves might survive. So when you see an enclave in the field, you can start to infer potentially what information you can get from that if you're going to try and use that to predict what that volcanic system might have done or what others might do. So again, it's what seems unrelated topic, but also still in this realm of fluid-solid interaction if we're trying to look at glacial firn. And so if folks aren't familiar with what firn is, it's essentially snow that's getting compressed and on its way toward becoming glacial ice, right? You have snow sitting here, snow, and then snow falls on top of snow, on top of snow. And so you get these layers of snow that get compressed and compressed. And so you have a porous medium, but as it's getting compressed more and more, that pore space, it coalesces till eventually you get to that point where it completely seals off. And these little air bubbles get trapped within this glacial ice. And so when you look at cores of glacial ice, really these bubbles that are trapped in there serve as essentially, records of past climate conditions. What did the climate look like thousands of years ago? And you can get these from these little bubbles. The difficulty is that we can date the ice that the bubbles are trapped in with a fair amount of accuracy, but dating the air is not as simple. And so what we're trying to constrain is what's the difference between the age of the glacial ice and the air that's trapped in them, so that we can try and match what we see in the ice with what we see in the air to reconstruct past climate records. And in order to predict that delta age with more accuracy, you need to be able to better constrain how long it might take air to percolate from the top of the snow through this porous medium, through this glacial firn, before it gets locked in to these bubbles in the glacial ice. And so this work I'm doing in collaboration with Kate Keegan. So she's a glaciologist. And so here she did these micro CT scans of these cores. And you can see as you go from 7 meters, 26, 70 meters, your pore space becomes much less. So what you're looking at is just these essentially slices through glacial ice or through firn, where white is the ice and then black is the pore space. And you can see deeper and deeper you go, you get less and less pore space. And so what we did is we took these micro CT scans, we essentially binarized them to either be black or white. So it's either pore space or ice. And then we feed this into the Lattice-Boltzmann method. And we're actually, in our simulations, we're using exactly the resolution that's being used in this micro CT. So we've got 50 micron spacing for our LBM cells. And then what we try and do is we model that pore space. So these are these different samples where we've taken the micro CT and we've reconstructed the pore space. And now we can use Lattice-Boltzmann to simulate air flowing through this. So in the simplest case, we can use it just to calculate what's the intrinsic permeability of this porous medium, and then use those measurements of the intrinsic permeability to try to estimate what might be the different times that it takes for different gas components or different components within the gas to essentially settle out to different depths or so. So anyway, again, this is just using the Lattice-Boltzmann method, but now we're applying it here to glacial firn because everybody is in many ways solving the same partial differential equations. And so there's that. And now a bit of a transition here, but still in the realm of looking at fluid-solid interaction and natural hazards. And so here I want to talk a bit about some of the work that we've been doing related to identifying flooding high water. And so here I had the opportunity to be part of the GEAR team that responded to these 2021 Western European floods. And so these floods were really quite substantial. I mean, over 230 people died during these events. And the losses were on the order of 46 billion euros. So really these events were extremely destructive. And I think this image on the bottom left here really illustrates this, where we're looking at, so this normally the R River would flow on the other side of this ridge and kind of wrap around this way and then come and flow around again on this side. But the flooding was so high that the water actually bypassed the channel in some amount and flowed through this tunnel here, and essentially blasted out through this tunnel as a high pressure flow. And there used to be a road here, all where this picture is taken from. There used to be houses all over here, and they just got blasted away by the water. So the destructive and erosive capability of this was really something else. And so during this deployment, we apart from the standard post-disaster recon work that we were doing, we also brought along a multispectral camera just to kind of test and see if we saw anything interesting. And so here you can actually see Nina Stark. She's holding the multispectral camera there, triggering it. It's normally mounted on a drone. So with the help from the Rapid facility, we kind of figured out how to take pictures on the ground with this thing. And so Nina's holding the camera and then taking pictures with her phone. And I'm essentially just walking behind her holding the battery. So you can tell who's the brains in this operation. But so I'll show you some images here where this is one of the structures that was damaged. And this is just a standard red, green, blue image, RGB. And you can see, maybe you can see the high water mark, maybe you can't. But so in the multispectral imagery, just looking at what the images look like, here we're showing these are the different bands. You've got these narrow band images, blue band, green, red, near infrared, red edge, and then a lower resolution thermal image. And the coordinates on the X and Y axes are just the pixel coordinates. But really what I want to point out to you here is that you can see in the multi-spec with different levels of strength, you can see the signal popping out that looks like maybe that could be a high water mark. And so based on these images, we kind of wanted to do a little bit more digging to see what we could find. And so we're looking at different band combinations where you combine the pixel by pixel reflectance from these different images. So you align them and then you do these differences in their pixel values. And so we're looking at above the high water mark, the red and blue reflectance was about the same. Below the high water mark, the red was not as strong due to the presence of moisture, water, so it doesn't reflect as strongly then. And so we took the difference between this red edge and blue band and just looked at what we could see in terms of the pixel values. And so what you actually see in this pixel histogram based on this combination is these three different modes. And so the first mode just corresponds to pixels in the sky. The second mode gives us these pixels along the concrete here, and then also reflection in the windows and so. And then the third mode contains, the pixels that we'd be interested in terms of looking at the building facade. It also has some other things in it. But this is kind of this third mode would be where we'd want to look to see what's going on. And so trying to filter out some of the noise, we use the normalized difference vegetation index to filter out any plants. And then you could also look at the thermal imagery. So you can overlay that thermal imagery on the building and you can see these different, the concrete here, the roof has a much higher temperature. And then on the facade, the temperatures are a little bit lower. See, the temperatures are actually higher here above the high water mark. And I'll talk about that in a minute. But so based on that, then if we filter, we can also try and isolate pixels with these, essentially this section here. But really, it'd be nice if there's a way that you could just isolate that to a single mode, right? Where you could take your pixel combinations and try and see, is there a way that I can do some type of index that will just give me one mode that isolates those pixels? And so here we're looking at this, we still kept this difference between the red edge and the blue band reflectance, but they normalize it by their sum. And then it collapses to the single mode. And if we plot the pixels only associated with the single mode, what you end up getting is this here. And so it actually matches the visual high water mark quite nicely. There is some noise, there's the shadows up top here, the shadows kind of throw it off. But for some preliminary work, it was pretty encouraging. And so we've been trying to push this work. And so one of my students here, Ananthaya, has been working on this, and she's been making great progress in actually trying to look at, is the signal present in other building materials? So she's been just soaking different building materials in water, taking pictures and trying to see how does the signal change. And so here, this is some of the work she's been doing where you have these different pieces of wood. And if you look at them, you had to pick, where the high water mark is, it's not, readily apparent. And just this blue tape over here is here where that's blue tape. It'll show up in the other images. It's not a processing issue. That's just blue tape that sat on there for a label. And then if you look at this thermal anomaly, you can see the temperature, what was, for what was dry versus what was below the high water actually pops up quite nicely. And then using that, she's come up with this cool zone mask and a way that then automatically fits this line across here to identify flooding high water. So she's been working on this, which has been really, it's been great. And what she did is she actually took some of the data from the reconnaissance we did for the 2022 flooding in Yellowstone. And so here's a building that was impacted. She isolated the facade materials, and then looking at this bounding box and applying this methodology from above, it automatically identifies where flooding high water is. So, she's busy working on this, writing it up. So keep your eyes open. Hopefully there will be something published on this soon. But I think there's a lot of utility for this for rapid post-disaster recon, for mapping flooding extents and intensity. And so paired with that, another question is when you're looking at flooding, right? Compared to earthquakes, we can get accelerometers, or we have accelerometers. We can kind of get a sense of the loading demand. For flooding, it's a little more challenging in the sense that, when you get to do post-disaster recon, the water's gone for the most part, right? So you don't get to see the flow patterns. But potentially using large-scale particle image velocimetry, we might be able to extract, at least coarsely, what some of those flow patterns might look like. And so this is just kind of an illustration of that case where we took some video from one of the bridges in Yellowstone that we looked at, or in Montana, I should say. This is Cinnabar Bridge. And you can see there's higher velocity here. And this abutment here was substantially more damaged than the left abutment. And if I show you here, this is a multispectral imagery where this is the same bridge we're looking at. And the river flows here, the Yellowstone River, but then what you're looking at, this coloration, is based on the iron oxide ratio. And so the basic hypothesis here for iron oxide ratio is that more clay-rich soils, so finer grained soils, will have a higher iron content. So their iron oxide ratio will show up higher relative to gravels or sands. And so if you look at this here, water flows in the Yellowstone this direction, and then you've got this gravel bar here that shows up, much cooler, so it's more coarse grained, and then you've got these finer sediments deposited on the backward side of this that have a slightly less blue color. But so the idea behind this work is that you could essentially try and use remote sensing to map the local geomorphology, because the way that the flow happened here and the fact that this abutment was substantially more eroded, if you look at the geomorphology, is not necessarily a surprise, right? You've got this gravel bar sitting here that's going to essentially armor this side, and then flow gets directed in that right direction. It gets directed toward this abutment. And so ultimately, that's where most of the damage would be. So if you can look at the geomorphology together with the flow conditions, and then where we decide to build things or how we decide to mitigate, you can look at a more holistic picture, because the landscape has been evolving for a long time, long before this bridge was put here. And so if you can try and tie together what you're seeing in the geomorphology paired with what potentially the demands would be, that would likely make for better mitigation strategies. So anyhow, with that, this work is never done alone. There's many, many different people that have been involved here. And so with the rock fluid interaction, I've been working on this for a while. And so Sonia is a new graduate student that just started on this, so she'll be pushing that forward. And then Jakob has been working on the Mayfic Enclave work, and that's together with Philip Ruprecht at UNR, and then Mike Lynn from the USGS. And then also with the multispectral work, here's Mira or Nanthaya. And then obviously, thank you to all the funding organizations. A lot of this work is funded by NSF. And then also GEAR for the post-disaster recon, and then the NHERI Rapid Facility and the NHERI Sim Center. And I've mentioned some of the GEAR work here. I know you also recently had a presentation by Alex Schuler on the recent work we did for the reconnaissance for Hurricanes Helene and Milton. And so that report will be coming out soon. You can also find the data set for the phase 1 and phase 2 deployments. I think phase 3 should be coming out soon too. But then also for the flooding in Germany and in Yellowstone, all that is available online too. And again, there's many people involved here. There's too many. I need many slides to fill this up. So I encourage you to go and look at the reports and look at all the people involved there, because these are essentially all the stuff. It's a team sport. And so with that, I'm happy to take any questions. Thanks for your time.
Thank you so much, Dr. Gardner, for the great presentation. It covers various topics that I think is really good for our audiences. I will welcome all people, if they have questions, to open their mic. If they cannot, they can simply put the question in the chat box, and I will read it for the Dr. Gardner, and we will answer. And also, I will wait for other. After that, I will ask my questions.
Thank you for your presentation. It was so interesting. I have a question about the measuring strategies that we can use based on your insight about the block block rock scour. When we have a slope that we have hazard of the flowing water over that, what type of measures we can use based on the scales of the blocks? And
Oh, right. Okay. Yeah. So if you're looking, so you're talking about water flowing over a essentially unlined rock, just over bare rock, correct?
uh, yes, generally,
Okay.
yes.
Yeah. So with those types of things, traditionally, right, people would have to go out there with a compass, get your Brunton compass, go out, crawl around on the slope and get measurements. I think if you have a rock mass that has some very clearly expressed jointing, then probably one of the best things you could do is you can use either photogrammetry, so structure for motion, or LiDAR data to extract that. And so we've done that for a number of spillways. And so actually Spalding was one of those that we did it for as well, where you can take your point cloud and then you fit a surface to that point cloud. And if you've used Cloud Compare before, it's an open source software that has a module in there that actually will extract based on your point cloud. You have all these planar surfaces, And then from that, it can actually calculate the normals to those. And so essentially your fracture orientations and their spacing, and actually a substantial amount of data that you could fit distributions to those results and do a stochastic type response. That's probably one of the most effective ways to do it. The caveat with that being that your fractures, if it's like if you think about like some of these igneous rocks, like for granites, granodiorites, like they have some nice, clearly expressed fracture sets that you could look at. If you're looking at something like a shale that's more closely bedded, then it becomes a little more challenging. And then maybe, yeah, trying to describe that using the LiDAR data or structural motion data may not be as effective. But I do think with drones, you can do so much more. That would probably be that would be my go-to for extracting structural data.
And what about the mitigation measures? For example, using bolts, something like that, to reinforce them against the flow.
Right. So for a lot of these, usually the solution is to put a whole bunch of concrete over the top of these things, and so putting rock bolts and then putting concrete on top is something that folks have talked about for some different projects. I think usually when you look at for scour, there's some recent work that was done by George Annandale that gets at this time rate of scour. Because I think the mitigation, right? If you want to put a bunch of concrete on it, or you want to put a bunch of rock bolts, you can certainly do that. And that's what people will do. I mean, if you look at you should look at the repairs that were done to Orville. It's really amazing the amount of concrete that got put in there and the work or so. But one of the big questions, and this is this work that George Annandale did, what it tries to get at is the rate. How quickly does this go, right? Because erosion's going to happen. And you're going to have different flow events. And so considering different flow events and their associated hydrographs, how long is your rock mass exposed to that flow? And based on that exposure, how long does it take? And so if you've got a spillway you're operating, do you need to fix this year, 10 years, 20 years, 50 years? What kind of problem is this here, right? Because there's a finite amount of money to be spent. But if you think about like for Orville, kind of I think brought scour to the forefront. And if you think about, how like if you have increased flooding events, you have a warmer climate, you have like in California, you have the snowpack, and then you have this warm rain falling on that, you can get substantial inflow. So maybe what your hydrograph might have been in the past is changing. So, I think, yeah, understanding the rate of erosion is probably going to be the first order question. And then once you understand the rate, then you can kind of decide, well, okay, well, what mitigation do I need to do and where? And usually that mitigation involves concrete in some shape or form. Now,
Thank you so much for your explanation.
no worries. Thanks for the question.
Any other questions? Okay. I'm gonna ask mine, and because of the time, I'm gonna restrict it to either one or two. My first question is that when you were showing that fluid equation and you were modeling those interaction, my question is that how much you can go complex on a particle that you are modeling. And by the complex, I mean both on the geometry side and also on the scale side, without losing that much on the computational efficiency that you were showing that.
Yeah. Yeah. So I think, one thing to point out with these methods is, the complexity that we're going in terms of describing the fractures and the individual particle shapes. It doesn't come for free, right? And the computations take a very long time compared to like if you look at some of the empirical or semi-empirical approaches, you can run those in a matter of seconds or minutes. These take, a few hours, depending on what you're looking at. And you'll only get, like we've run something with a few hundred particles. And the computational demand there is not really the particles, but it's on the fluid side. Because if you're trying to resolve, like if you think about the characteristic length for your particles, if you want to resolve, because how well you resolve the hydrodynamic loads on your particle is directly related to what's the mesh discretization for your fluid surrounding that. So if you have a characteristic length of L and you chop that up, that you have 10 10 fluid voxels for that, then we've seen like 10 to 15 is where you get decent resolution of your solid in the fluid domain. And so the difficulty there in scaling that up when you look at a whole until quantum computing becomes a reality. You couldn't do a full spillway, but what you can do is you can do smaller element level tests and try and query the uncertainty in that and the variability and sensitivity based on what you see in different parameters. Now, in terms of the particle shape, for the rock blocks, we've used polyhedra just because if you look at for the types of rocks we've been looking at, generally those joint sets will cut these polyhedral blocks. And so we wrote some software that can take that structural data from your field observations and generate a 3D fractured rock mass. But I didn't put it in here, but I should have. There's a simulation where we took some micro CT scans of some quartz particles and just let those settle through fluid. And so you've got essentially there you can do an arbitrarily complex shape. You can import those shapes, and then just it comes back to what's your mesh discretization. Because if your mesh is really fine, you can represent an arbitrary shape with pretty good accuracy. So yeah, does that answer your question? Sorry, did you all lose me there for a second?
It was for a second, yeah.
Okay, so did that answer your question, Parissa? Or
Yes, I have the answer to my question. And thank you so much for answering that. And as a matter of fact, I would encourage people, if they have any questions, please reach out to Dr. Gardner. Thank you so much, Dr. Gardner, for being in our today meeting. It was really informative and I enjoyed myself a lot. By this, I will change the gear of today's presentation a little bit to
excellent. What I was just going to say is thank you so much for having me. I really appreciate it. And also, if you have any questions, don't hesitate to reach out. I'm happy to talk more about these things. And again, thank you for the opportunity.
yeah, thank you.